Okay, I am now recording. Who else do I have on here? Hello, Renee. I see you there.
Sir.
Okay, today is Thursday, May 3rd, 2018. This is the normally scheduled class of the ITSE 2309 database programming. This will also be the last regularly scheduled class. I may do a recording with respect to the final, and maybe I need to turn on the overhead. Today we're going to look at several things. We're going to talk about the unique constraint. We haven't talked about that. We have talked about not null primary key. We've talked about a check constraint, and I guess I'll wait for that thing to come on. We'll talk about, let's see, the primary key and the unique are called table level constraints. There we go. And I'm going to talk a little bit today about some other options on the foreign keys. We're going to have what we call cascade, on delete cascade. In other words, if you delete the parent key, you have some options on what happens to the child key. I recommend you be very careful with cascade. So if you create a foreign key, and you say it's a foreign key, references table parent key, on delete cascade. That means that if the parent key is deleted, the child keys are deleted with it, the child records. That can be dangerous. There's two other options, but the most common one is you have to deal with it. You have to go to it. We'll talk about sequences.
I tried to watch this video this weekend, and that link is broke.
This link right here?
I couldn't make it work. Yeah, that's what I'm getting. Searching online. I did. No, I gave up right there. I didn't go any further.
Okay. Thank you for bringing that up. I try to check these links every so often. I've been told that the link is broken here, and I will figure out where it is.
Sorry to know.
Yeah, well, that's something we need to know. Database indexing. Database indexing makes the query fast, a little bit like a high-speed. If you, I don't know if you've ever programmed a alarm system or something like that that has to have high-speed response. So you program a zone as having high-speed response, and what that does is it steals cycles from the other zones. So by making it fast, you necessarily make other things slower. And a database index is a little bit like that. Index, it makes it fast, but how does it make it fast, and why does it make it fast, and at what cost does it make it fast? And the cost is fairly great. Now, creating an index is, we're going to see, very simple. Create index, give it a name, on table, one or more fields. That's simple. Now, there are some other options. You can give it parameters like a clustered index. Well, a clustered index means that the database is stored on disk by that index. That's the fastest possible index. You can only have one clustered index, and by default, that is your primary key. So usually you don't create a clustered index. A primary key is a clustered index. That's how it's stored. Sometimes the primary key isn't very important. Sometimes you want a different index that you're going to use more. Primary key might just be a timestamp when it came in. So an index is very simple to create, but they are very demanding in terms of the resources of the database. say an index, think about it like searching a printed telephone directory. I'm going to go on to the next slide. Think about an index like an old card catalog. Have you guys ever seen one of those? Well, you laugh. Lots of people today haven't. Okay, everything is computerized. So it's.
You ever go to the library and find a book that way?
Go to the library and find a book in one of those.
But I don't think I've done it myself.
Well, back in the old days, that was how we did it, and it's very much the same sort of thing today. Yeah, don't drop one of those boxes. The librarian will be mad at you. So if you were to open the catalog and you were to look in there, you would see here. Yep, well, I guess that's in German, isn't it? Okay. I don't read German. Now, there were 3 index that were usually indexed, and these included what? The title index, the author index, and the subject index. So if I wanted to find a book, Moby Dick, okay, so I would look in the title index because that's the title, and there might be more than one book with the title Moby Dick. There's nothing stopping somebody else from writing one, or Moby Dick and how it was written or something like that. If I wanted to find all of the books by Herman Melville, I would search the author index in there, and I would find Moby Dick and 3 years, or what was it, 7 years before the mast, and Billy Budd stories and all of that. No, that was Milton. And the subject index, fine. If I wanted to find everything about whales, I would look into that, and I would find Moby Dick, and I would find textbooks on cetology and Jonah and the whale and all that kind of stuff. First search the title index, and then I'd go straight to where the textbook is stored, and it would be a whole lot faster. Now, you've heard about the dictionary for masochists, have you not? You're about to. All the words are there. They're just not in any particular order. Okay, so how do you find the text, word in that dictionary? You just have to start at the beginning and look for it. Well, what would you do if you needed to find a book and you didn't have an index? You would start at the beginning of the library and go until you found it. Now, that would be somewhat time consuming, but remember, you can look at 4 billion books a second, roughly. Well, maybe not that many, but you can go fairly quickly through that, and a lot of it is in memory operation. So as fast as you can move a page into memory, search it, and move the next page in. So you could find in a library, you could find a book in a few seconds if you had to do a table scan, if you had to just search for it. But an index makes it a lot faster, because how many did I have to go down through there? Well, the page, the book, I looked up one page and then I went straight to the book. Now, if I had a really, really big index, I might have sub-indexes. So I might have one index that took me to the correct index for where that thing was, and then in there I would find another index that took me to the correct drawer, and then I would go out to so I would have 2 or 3 indexes to search, which is typically the way that this happens. But anyway, it's very much like this. Now think of the cost of this. Well, the cost of the size of that thing is not insignificant. That's probably a fairly small library. And I was kind of curious, that looks like a computer monitor up there on top of it, or is that a picture? I don't know. But this thing takes up a fair amount of room. In a large library, they could take up an entire room themselves. So they take up space. They also impact they have to have librarians that maintain them. Every time a book comes in, it has to be added to the index. If they reorganize the shelves, they have to reorganize the index. If a book goes, if a book is deleted, the index has to change. Okay, so the indexes are very expensive. They don't come for free. They don't come for free in a computer either. So we have indexes on title, author, and subject. Okay, here's some examples. What if I wanted to find a book that contained 376 pages? I want to see all of the books that have 376 pages. Is there such an index? Do you think there is? We have title, we have author, we have subject. Is there anything on the number of pages in the book? Now, that information is probably in the database. I'm sure that is, I'm sure if I went back and looked at that card carefully, it would probably tell me how many pages are in it. But that's different. 1934. Okay, it doesn't, but it could. So that information being there is fine, but we don't have an index where I can look up, 376 pages, and then next one is everybody at 377 pages. Why not? Okay, good. That's what I'm looking for. Nobody cares. When was the last time you went to a library and you wanted to read a book that had 376 pages? Nobody wants that. It's silly. It's a silly idea, but that is an example of we don't build an index on everything. Just because we have it in the database doesn't mean we're going to build an index on it. There's lots of things that we just aren't going to search on very much. Okay, somebody's middle name. Some things we are, a person's name, last name, that would probably be a good index. But something like your street address, probably not, unless it's a very specialized database. Okay. Indexes are not free. Here's the big one. Nobody ever searches for a book that has 376 pages. We're not going to build an index. Example 2. I like this one. There's my good prose here. Suppose, just for the sake of argument, that we could judge a book by its cover, and we really did want to search by the color of the cover. And let's say there's only 3 primary colors, black and white. So there's what? Red, yellow, blue, black, and white. There's 5 colors of covers. Might we build an index on the cover's color? Even if we did want to search for all of the red textbooks, would we build an index on that? The answer is, if I go to an index, I'm going to have to search that index. That means that I have to go in there and find the right drawer and find the right card, pull out the card, go to the shelving and find that book. What are the chances that I'm going to have a red book on every shelf in the library? There's only 5 different colors. The chances are very good that I'm going to have a red book on every shelf. Okay. We're having a convention here called the National Rifle Association, and their position is that if they go to background checks, the government will know where the guns are. There's guns in every house. I mean, what difference does it make whether you have an index or not? There's red books on every shelf. So the fastest way to collect the red books is just to take a cart and go down the shelves and check pulling the red books off the shelf. Because if I start running up and down the aisles to the using the index, it's actually going to slow me down. Some things may it has what we call a very low cardinality, is the way we would say it, meaning that it's only got 5 different values in that field. So the chances of there being one of those 5 different values on every page of the database are very high. So searching on the index is just, chances are if I just start and just go through it, I'm going to find them a lot faster. Things that make good indexes are things that are Every time I say relatively unique, people say, no, unique is unique. It's not relatively unique, but relatively unique, meaning it has a very high number of different values. Chances are somebody else in the world has your phone number or could have. That's fine. I think of something different. There's certain things that are not guaranteed to be unique, but they're pretty close. Your driver's license number. Somebody in another state might have your driver's license number. It's possible. Now, for a state and driver's license number, it'd be unique. But let's just on driver's license, that would make a good index. Zip code. If we talk about the city of Frisco and everybody in the city of Frisco, and they have a zip code, would zip code make a good index? Well, I don't know how many there are in Frisco. If I were guessing, I'd say 20. That's a very, very low number. Okay. For a good index candidate, I want it to return no more than about 1% of the database. So if there's 20 zip codes, each one of them is going to return 5%. That's a poor candidate. Okay, example 3. Sometimes books come with abstracts. These are a one-page synopsis of the book. Should we index the abstract? How big is an abstract? Well, typically a page or 2. Remember that I have to, in the index, if we went back to this index and it's a title index, notice I had to put the title onto the index. So the index had to contain the book's title. Therefore, the index will contain the full abstract. Anything that is very large, I want my indexes to be as small as I can. Now, this doesn't say that I can't index the abstract, but the chances are very good that, first of all, people aren't going to remember the whole thing to type it in. And there are search engines built where every word is indexed. For example, Google. You start typing words in Google and it figures out what you're looking for pretty quickly. And that's a very sophisticated database. But no, we would not build it on the abstract because it's too big. I want something small, so for a primary key. Library system has to track materials being checked in and checked out. Should we index the field that records the checkout status of a book? This is a good example. So I've got a book is either checked out or it's checked in, and I'm quite sure that that's in the database. Should I have an index that records the status? Let's say I have more than one checked in, checked out, on hold, checked out to a professor who's going to keep it 6 months, past due. Yeah, lots of things, let's say. Would I want to put that as an index? Answer is no. Why not? It's changing all the time. The book's title doesn't change. The book's author doesn't change. The book's topic doesn't change. For an index, I want something that doesn't change. Could you imagine going down to the Social Security Department and saying you're tired of your Social Security number and you'd like another one? They're not going to give you another one. And that's an index. Okay. Have to update the index if it's constantly changing. I'm saying here in reality that table is so important to the daily function it will be indexed, but the example still holds because I have to be able to find the books quickly wherever they are. So my guess is that in a library that would be indexed. So it depends on a lot on what you're doing. Okay, here's a few general rules right here. Don't index fields that are searched infrequently or little bitty tables. If you only have 300 or 400 rows in a table, don't worry about building an index. Unless It's for our table, like we only have 114 rows or something. I would never build an index on a table that small, but I will just for the fun of doing it once. Do not include fields that have very few distinct values. We call this a low cardinality. Very few different values. Something that is either true or false is a terrible candidate for an index. If by specifying one value, we will return over 5% of the database, 5% is the cutoff pretty much. If it's over that, it's a bad candidate for an index. So we have to have at least 20 different values in there. And I would hope to have a lot more than that. I would hope that I would return 1 or 2 or 3 records out of thousands in the database. We try to build indexes on fields that are as small as possible. The values will have to be reproduced in the database. So if a field is large, if it's a big varchar, that is a poor candidate for an index. We want something small. And we want something that is static. We want something that is not going to change. There I'm talking about ask for a new social security number. They're not going to give you a new social security number. You're stuck with the one you've got. Let's see what we've got. Okay, here is a demonstration table that brings in a new one. Here is a constraint in there. Constraint demo unique. The constraint is unique. We have not seen that one before. So I have one that is a primary key and one that is unique. Now, if that field demo2 were also constrained as not null, then we are looking at a primary key essentially. And remember what the 3 rules of normalization were. The key, got to have a key. The whole key, you have to use the whole key and only the key. Remember those? So if I had a field that was not null and unique, I would essentially have a second primary key. And I would violate that third normal form. Sometimes you do. There's nothing special about that third normal that you have to get there. But this is unique. Now, point out this. If you have a primary key or a unique field, it is already indexed. When you think about it, a primary key has to be unique. And of course, if you put a unique constraint on it, it is unique. Every time I enter something into that field, I'm going to have to search to make sure that I keep that unique constraint. And so that implies that there's going to be an index built. It already has one. You don't index a field that is unique or a primary key. Okay, when we get to the index, syntax of creating an index, nothing to it. It's that simple. Create index, give it a name, on, table name, in parentheses, field name. Or field names. It can be on more than one. If I want to, if I've chosen my field correctly, I speed up by orders of magnitude. If I chose my index poorly, I can slow down the database and waste disk space. I'm losing my voice tonight, I fear. Review. Frequently searched. Foreign keys tend to be very good candidates. If a foreign key meets the rest of the specifications, then it's probably a good candidate for an index. Almost unique. meaning that when I specify this, I'm only going to get 1 or 2 or 3 or half a dozen records returned, and I can easily search through them and find the one I want. For example, if you go to the pharmacy, they ask you for your name. Well, your name might not be unique at the pharmacy. Then they ask you for your date of birth. Your name and date of birth together are, you better believe, an index. Are they guaranteed to be unique? No, but they'll narrow it down pretty well. Police databases will typically run by the date of birth, and they'll get it in a range. Well, we think this guy's 28 years old, and they will also have in there their known street names. Okay, so, and that's indexed. So I want to find everybody whose street name is Snake and was born 27 years ago, plus or minus 3 years. Okay. Almost unique. I like that. I like a small scalar. What is scalar? Scalar means that any two of them can be compared. So a number is scalar because given two numbers, one's greater than the other one, it's the other way, or they're equal. Okay, letters and character data work the same way. It can be compared. If I can compare it. What isn't scalar? If I just have something that's just ordinal, like, Robin, Blue Jay, Redbird, Cardinal, and they're just titles I give to things, that is non-scalar. I like static data that don't change very often, not a primary key. If it meets those guidelines, I'm going to consider an index. Just bite the bullet. Index is going to get big. I have one I do. I don't think I'm going to do it tonight because I'm losing my voice tonight and I don't have a whole lot of people here. But if I had more time, I would go into exactly how a database is maintained, how big will they get, how many gigabytes of data. If we have a database that has 1 million records in it, how many gigabytes of data do we have to index that? And you're going to find it's a significant amount of data, amount of disk space. Probably, it's hard to say exactly because it depends on the size of the index that you're using. But if I have a small index like a social security number, it's probably about 8% of the database, of the size of the database. Now, it has to do with the size of the index and the size of the record, of course. So I can't say it's 8%, but 8% would not be unusual. Okay, well, I'm going to talk a little bit about indexing. G. This is the B+ tree. Is a monstrously complicated data structure, and trust me, if you are a computer science major in about your junior level weed out class, upper division, one of your first upper division classes, they will give you a B+ tree to write, and you'll be dreaming about that. Notice that it has a root node, and in here, so for example, this is the index value 19. If I want to find anything less than 19, follow this link to that web page, to that disk page. If it's 19 or greater but less than this one, I follow this link. Down here, I find 5. If it's less than 5, go down to this disk page. And there I find my 2s and my 3s and 4 and 1. And now I can go straight to the record. On the other hand, if it is from 5 and less than 13, I will follow this one and I will find my information down on this disk page. So notice that I go through 1, 2, 3 levels. It takes me 3 disk hits to find it. Okay. And so what's a disk hit today? How much time does it take to get something off of a disk today? Well, the root is almost certainly in memory. So it's probably 2 disk accesses. And a good disk access today is about 5 milliseconds. And you want a good fast disk for database. So you probably are looking at 10 millisecond access to get to the record you want. Compare that to having to do a table scan, and you see a table scan could easily take you 35 or 40 seconds. I'm going to let you talk about this. I'm going to let you read this. Estimating the disk needs gets a little bit dry. How big will the index be? In a half a gig table, there are about 125,000 disk pages at 5 millisecond access. If we had to go all the way through that table, that half gig table, it would take us about 625 seconds, or something on the order of 10 minutes. On the other hand, using an index, if I've done it, I will get to a single record in 2/10 of a second. Excuse me, 2/100 of a second. And then we do our review again. I don't typically ask about a B+ tree. Indexing quiz, okay. Indexing, this is another one that's similar. Goodness. Okay. There is another one that I wanted to work with some. And let me see if I can find something online quickly. Start with increment by min value, max value cycle. Okay. In its simplest form, it's just simply create sequence. My sequence. Okay. No, this is something different. Okay. Now we're used to having something that we call a identity. Remember that? Or an auto number. And I told you I didn't like auto numbers, or as we call them in SQL Server, identity. I'm just going to mention this briefly, and then we'll be done here tonight. Okay, a sequence is kind of like take a number. It's another database object, and if you go to the butcher shop or something, you take a number, reach up and pull a number off. That number is unique. And no other person will get the same number. So if I pull the number off and I take a 7, and you come along and pull the same number, go to that sequence and pull the number off, you're going to be different from mine. So this allows me to generate unique numbers. I don't have to generate them in order. Okay. So create sequence, my sequence. I just want to be able to work with it here. When I do this, okay, created the sequence. Let me see what I've got here. Control. Um, no, that wasn't what I wanted. Select. Well, I'll get it done in just a second. Okay. There are a few options I have. One, I can give it a start with, so I can tell you to start at any given place I want it to start. It does not have to be 1. By default, it said starts with 1, but I can start with anything I want. So I can start with 13. Okay, and it has to be an integer. So if I select something from this sequence, if I take a number, the first person to take the number will get 13. Next person to take the number would by default get 14. If you and I both get there right at the same time, one of us is going to get in there first, get the number, and the other person will get the different number. So I can start with 13. So cannot drop the sequence. Okay, why can't I drop the sequence? I guess I need to go. Okay, increment by. Whatever. INCREMENT. Don't know why that's not turning color, but I'm thinking it should be. So so the first one will be 13, and then 20, and then 27, and then 34, and go on like that. So I'm free to do that. The other thing I can do, I can take several sequences and build keys with multiple fields in them from these sequences. So it's guaranteed to be unique. Let's see, what else do I have here? Increment by. There's a minimum value and a maximum value. These usually are not specified because they are very, very big. They're like a very long integer, so they can get very large. Increment by can be negative, so I can start with a very high number and decrement it. Cycle, if I specify a cycle, so for example, I could say a maximum value of 100, minimum value of 1, and I want it to cycle. So I would get 1, 2, 3, 4, and so on up through hits 100, and then it drops back and cycles again. If I say no cycle, it just stops. Next one is kind of interesting. We have cache or no cache. Cache, how many? So for example, I could say cache cache 10. That means that when you take a number from my roll of numbers, I'm not going to give you one number. It takes me, hey, can I have a number, please? I have to stop what I'm doing and go get you a number. Chances are you're going to want another number pretty quickly. So what I'm going to do is get you 10 numbers, turn them off and hand you 10. All of those numbers they're for yours to use, and they're going to be unique. Okay, they're in this session. Now, when you end your session, they no longer hold, they go away. So that's one of the bad things, but it's the same bad thing about an identity. If you put a record in and the record does not stay or something, you escape, that number is never used again. Okay, let me see if I can get this to work. Select my sequence dot. Okay. Next val doesn't appear to be working. Let me see if I can get it to work. What I was trying to find on Google okay, I think this is it right here. Sequence dot next val. Okay, I did that. Let's see an example. Okay, select. Oh, that's Oracle. Yeah, Oracle. Oracle does it slightly differently. That's Oracle again. I'll have to read that. I usually don't get to it, but I think I'm gonna go ahead and end there. The sequence allows us to basically create a take a number, and then based on that, I can say select my sequence dot, and I believe the word I'm looking for here is next val, and that gives me the next number out of that sequence, and nobody else will ever get that number. I do not have to go in order through them. I can randomize them so that you don't know exactly that what you're going to get, but you will get a number that is unique. The most important thing today,
W3 Schools is showing it to be
auto increment. What?
I don't know.
I haven't. I've always seen it called next val, but yeah, I could just be tied strictly to Oracle. I will.
Is that pure SQL then?
Well, no, it is pure SQL, but it's one of those places where the various platforms will differ on how they do it. For example, dropping tables and things like that, and the go command, to break it up into different batches are different. So anytime you move from one to another, there's really no such thing as being able just to take a complicated script and just pick it up and move it to another platform. But each individual piece of it should work. I'll continue to work on this. I'll try to get this sequence working. But basically today we talked about the index, and I believe that the the assignments accounts payable system in third normal form. This is pretty easy. The assignment is really pretty easy based on what we know about the way these tables are used. Write the SQL code. Well, duh, that's pretty easy. Create index, give it a name on the table and the field. I would say at least one index per table. Maybe let's say 5 indexes. It doesn't have to be one per table. Do not index primary keys. The primary keys are bold. Okay. If you have a foreign key, that is a good candidate for an index, given that it has a good cardinality. One of them in here that does not, for example, would be default terms ID is a foreign key, but there aren't very many in there. And so this just basically asks you to create some indexes. They're very easy to create. You drop an index just like you drop a table. You just create index, you give it a name, on. Okay, so I can create an index. Okay, foreign key, probably a good bet. Then that should create the index. Let's check it and see. It's really that easy. So underneath under the covers of this, I'm thinking in terms of what indexes I want to create. And that's what I'm asking you to do here. It is a fairly easy assignment. And so this one.
What's the rest of the story? Can you then do a select statement on the index?
They are transparent to you. You shouldn't know they're there, except you see that your tables are now running faster. Right, so the system will use the indexes, but you, the human being, have to decide where to put the indexes because you know what fields you're going to be searching frequently. Now, you have a way to get, and that's the topic for the next class, you have a way to gather statistics on your tables, and it maintains them for you. What's being used a lot for searching? What are my people doing out there? And so I can get how many times am I searching this field? So I find a field that is not indexed, it's just getting searched all the time. That would be a good place for an index, given that it met the rest of the criteria. Big, well, primary keys, it's already got an index, so they're not gonna be searching a field that's got an index. They'll be going over to the index. Primary key's got an index. It's got high cardinality, a lot of different values, and not a really big table there. So chances are that if it's getting searched a lot, it's a good hit for an index. Indexes have a cost. Okay. Now I'm going to, let's see, what time is it? It's about almost 7 o'clock. We're going to break down. I'm going to leave the Zoom turned on. I'm going to end the recording. And unless I need to turn it back on for some reason. If somebody online wants to ask a question, I'll unmute the microphones online so you'll be able to talk through my headset. And let's see. We will do that. We will have the final exam will be next week. I will make an announcement, and I will probably do a Zoom presentation on it. So this won't be our last Zoom, but it'll be our last class meeting. Let's see, read the announcement that I put out about the final exam, and all of the, well, most of the grading is done. If you're in the WWW class, I haven't finished up that grading. I'll finish it tomorrow on the train. For my 2 face-to-face classes, I'm pretty much got it caught up. One thing that is important is that my grade book at this time is not set to treat late ungraded assignments as zeros. I'm going to change it such that it shows you anything that you don't have turned in. Instead of just not counting it, it counts it as a 0. I've had people come up with a ugly surprise at the end of the semester when it all turns into zeros. They say, but wait, I thought I had a 90. Yeah, what you turned in. So I'm going to change that. Please don't scream at me if you turn in something and I'm a day late getting it graded. If you turn it in, now the deadline will be 1 week from tomorrow at 6:30 p.m. And I think I'm being pretty flexible on that, about that, or by that, but I'm not flexible on that. 6:30 is absolute. I will not take it at 6:31. Okay, so don't get caught with anything that I've been working on for a long time, and oh my goodness, it's time to turn it in. Okay. Okay, I'm gonna unmute. Unless you have your microphone turned off, you may speak to me. I have my headset on.
That's okay. I am going to finish up what I need to do and submit my work.
Okay, is this Renee?
Yes, it is.
Okay. Okay. If you need to get my attention, send me a message on the inbox, in my inbox here on Canvas. I'm going to leave this up. I'm going to turn off the recording